All right, in this video, in 13.7, we're going to talk about differentials for functions of multiple variables. And the idea with a differential in Calc 1, recall, was looking at the change in our function in differential form, right? So if I increase x by a little bit, we'll have a true change in our function, and then we could approximate that true change with the change along our tangent line for a function of a single variable, and that change along the tangent line we called the differential change. Well, same idea here for a function of more than one variable, right? So let's say I have some surface here defined by z equals f of x, y, and we're at this point directly above P with coordinates a, b. And let's say I want to increase x a little bit and increase y a little bit, and we're going to move to a neighboring point, and I want to measure some changes, right? So, for example, I move dx units to the right of the point P, and then dy units up in the direction of y, and I could go ahead and look at our tangent plane here in green as well, just to fill that in, right? And this thing is going to give us an approximation to our surface nearby this point here in red. And there's really two changes I could consider now, right? I could consider the true change in my surface. I'll call that delta z. That's the true change in z. But if I just looked at the change along my tangent plane approximation, right, I'm going to call that the differential change, just as we did in Calc 1. This is called dz, right? So that's just giving us an approximate change in z. Okay, so how can I go about computing this thing? Well, now, right, we have to take into account the fact that as we move in the x direction dx units, there's going to be a little change in z that amounts from that. But then also when we move in the y direction, there's going to be a little change there. And the total differential change here is going to be the sum of those two individual changes. So looking down here, I say that the differential of z equals f of xy at the point P with coordinates a, b is going to be, well, dz equals our partial derivative of f with respect to x times this little incremental change in x. So think about this as like just measuring this little rise along this piece of the tangent plane running in the x direction. Okay, so this is just like the slope in the x direction times the run, and that product will give you this little rise. Then you're going to get a similar change, but in the y direction. So it's going to be the slope in the y direction times the run in the y direction. So this product tells me the change in the y direction. And then the total change here would just be their sum, okay? So now what I'd like to note real quick, and then we'll look at problem 3 on the worksheet to illustrate how this computation will work. Okay, the big takeaway here is that our true change, our delta z, this thing will be at least approximately equal to this differential change dz when what? Well, when our incremental changes dx and dy are reasonably small. Okay, so this is really, really similar to that result we wrote down in the intro video looking at Calc 1. Okay, all right, so now let's see this in action. So question 3 on the worksheet just says compute the differential of each function, and we're just given 3 functions here, and we're going to compute their differentials. And notice it doesn't specify a point, so I want these differentials really to be valid at any point x, y. So for example, like let's say I'm looking at f here. Well, first off, what's just fx at any point? That would be 2x. And what is fy? It's 2y. So here's how this differential is going to look. It's going to be d, and I could call it dz if I wanted, but since the function's presented as f of xy is blah, I'm going to say df is equal to what? Well, I'm going to take the x derivative, which is 2x, and then I'm going to multiply that by the little change in x. And then I'm going to add to this fy, that's 2y, times my little change in y, that's dy. Okay? And that's it. Nothing to it. All right, for B and C, pretty much the same idea there. So here we would have for our fx, well, 2x e to the 5y, and our fy would be, don't forget the chain rule factor here, would be 5x squared e to the 5y. So then there we're looking at, and I will write dz here just because the way the function's presented. So this would be 2x e to the 5y times your little incremental change in x dx plus the 5x squared e to the 5y times the little incremental change in y, which is our dy. Okay, and there's that. And then last up is C. G of xy is 1 minus 4x squared. Okay, so here notice that gx now, gx is minus 8x, and what is gy? 0, right? Y is independent of, g is independent of y. Okay, so then what would the differential of g look like? Well, there I would get dg, as I'll write it, is simply minus 8x dx, and that's going to be it. Notice, since g is independent of y, right, the change in g will be totally dependent on us changing x. Any change in y won't change the value of g. So that makes a heck of a lot of sense. All right, well, we'll pick up with more of this in the next video. See ya.